So this is joint work with a couple of my colleagues, John Aycock and Sarah, who's in the back of the room. So before I begin, I want to, sort of point out that even though I've been to grad school, I still feel like it's very difficult for me to believe in things I can't see. And so I think this is, part of my instinct is, well, we're interested in memory events for many different reasons, including offensive security and basically analysis, right? So I think analysis is the root of many offensive security techniques, right? In other words, imposing some sort of structure and understanding on large opaque data artifacts. So I think that's maybe the relationship of what I'm going to talk about to offensive security. And so, there are some ways of viewing memory events or memory activity of programs and processes, but they all have their pros and cons. And so we couldn't, it's not easy to see memory activity in a process. And so because of that, we built something to see these things. Okay, so I'll tell you about our system Cage. This is purposely blanked out. You can try to read it if you want to. I'll tell you about Cage in a second, but before I do that, let me convince you that memory event analysis is indeed a challenge or an interesting problem. And so while that loads, 2.0. So this is the memory activity of a process, and $20 to anyone who can guess what process this is. Takers? No. No. All right, 2 guesses is all I get. I'm in danger of losing my money. This has been true. Okay, so yeah. Been true. This is about 190. Some of it you can't see, right, because the contrast is bad. But there's 119,000 events depicted in this picture. And you know what? Maybe you're really good with awk and GraphViz, and you can slice it down slightly, but I don't get too much more information from this version of events either. All right. So we're dealing with high rate. I'm not going to say big data because that's a curse word, but we're dealing with high rate sort of data artifacts here, quite complex, right? There are actually all sorts of interesting relationships here between code and data and whatever else. And so wouldn't it be nice if we had a principled way, a structured way of looking at and examining and filtering and manipulating these events? Okay, and so on the one hand, we have this really complex data artifact. On the other hand, I think we have many, computer scientists and students who may be lucky that they even get this view of a process's memory. All right, so I mean, just this is the process address space, as it were. In other words, an enumeration of the memory regions of a process, happens to be bash on Linux. So we're lucky if people even get this understanding of the structure of process address space, let alone understand the events that emit from the use and the interaction of all these sections, right? So this was kind of the problem we were trying to tackle, and we implemented a kernel-level mechanism we call Cage. And Cage is quite useful for not only monitoring the events that a process emits, but also modifying them in flight, which is pretty cool because you can rewrite behavior on the fly as well. And we wanted to not only intercept and examine these events as they were occurring, we wanted to export them in a fairly convenient way. And so the particular avenue we chose is via a network device, right? And so, as Julian said at the beginning, the neat little twist here is basically you can just fire up Wireshark and dump the memory activity of a program as it's executing, or save the captures for offline analysis later on. And there's a cornucopia of ways to examine this information. Just a few of them we've done already. Finding a private key in an SSH client address space. You can overwrite data or instructions, obviously then modifying whatever the program is doing. You can do other cool things like find all the buffers in a program, right? So I think what we've built is a pretty interesting microscope, and what you can do with that microscope are many different sorts of things. And so, maybe what's the hook? What's the key insight here? Why Wireshark is this? As I said before, is just this neat, cute twist? Not really. I think what our insight here is to purposefully adopt the metaphor that memory activity is like a network packet trace. Okay, and then by adopting this metaphor, what we get is the benefit of being able to filter and manipulate this information stream in all the ways that you can with existing network packet filtering languages. And what we have in the system are actually 2 places where you can do filtering, and this is not just because we didn't want to do one. we can pre-filter events as they're generated. And this is actually quite useful because we can throw away a whole bunch of events that are high rate and would overwhelm later stages of filtering like Wireshark. And then we can, of course, post-filter in Wireshark. So for the next couple slides, I'm just going to describe, Cage at a very high level. The details are in the paper. And then for the remainder of the talk, I'll walk us through a very simple example of Wireshark locating the SSH key. Right? So people have done this sort of thing before. We're not claiming to be the first people interested in memory trapping and things like this. But what we realize is, as we went through the process of designing and in some cases re-implementing some of the mechanisms or techniques, this is actually fairly difficult if you want to get it right and if you want to be relatively low impact on the processes you're monitoring, right? So this, for us, was sort of a useful experience report, and that's one of the reasons we're sharing it with you. And by the way, all the code is up on GitHub and whatever else. And one of the other things we've done is validated on a number of different virtualization platforms and whatever else. This is also sort of non-trivial in demonstrating that whatever mechanism you do provide, I think there's a legitimate question as to how widely applicable it is, right? But our respect to the folks who've done other memory analysis stuff. Cage, fairly small. I mean, people can argue about whether 1,000 lines of code is small or not, but fairly lightweight impact on the existing kernel, right? We add a few pieces of functionality. Mainly the changes are in the page fault handler and the debug handler and stuff like that. I'm not going to walk you through this. Unfortunately, this didn't make it into the paper because about a week ago we sat there and said, well, how will we explain the system to someone? And then we came up with this, which is actually a pretty good diagram of how the system behaves, and unfortunately we didn't think of it before we wrote the paper. But there are basically three important events of interest, right? An instruction is executed. That instruction may be marked as caged, and then that's the middle of the diagram. Basically it is then handled by our system, and you can see sort of toward the right-hand side of the picture, that event is wrapped up in our memory packet format and emitted to the network device. At that point in time, we can actually filter or change it or overwrite it. And then just some technical details. The instruction needs to execute, as is standard, and we need to recage the instruction after it finishes executing. Right? So those are sort of the three main streams of events going from left to right. We have a number of interesting BPF filters, and this is maybe where we can talk offline about some of the interesting things you can do with BPF. For the rest of the talk, I'm just going to focus on this penultimate one, buffer viewing filter. Right? So what I'm going to show you next are two sequences of Wireshark screen caps. Sarah's here with the laptop. We can certainly give live demos later, but we didn't want to suffer from the demo effect during the talk. So this is an illustration just of an instruction of interest. So we know this is an instruction of interest because it's manipulating the buffer we're going to be interested in later on. And so this is the information that Cage will export over the network interface, and we can dump in Wireshark. And as is normal, so those of you who look at network packet captures, right, this is sort of par for the course in understanding here's all the fields involved in the packet and the raw dump and whatever else. And so this is just showing the corresponding parts of the event that we're exporting. Right, obviously you can see the data at the effective address, which will become interesting later, as we'll see. But of course, we get all sorts of other interesting information about the memory event. Some of these have an interesting backstory they don't quite have the time to talk about. But I'll point this out, that one of the nice things about treating this as a network protocol in some sense is we can reserve some fields and then have the flexibility to expand their meaning later on. And this is exactly what happened with this flag field. At a certain point in time, we wanted to know, hey, is a new VM area created or not? And it was almost as simple as dedicating this bit to tell us that that's that type of record. I'll skip some of the other stuff. So what's nice about this BPF filter is that we've noticed previously that this RAX the register had the address, the dynamic address of the buffer we're interested in, and so the BPF filter has extracted that piece of information and is now dynamically watching for a future access to that buffer, and that's what this series of screenshots shows you. And interestingly enough, of course, the data at the particular effective address starts off SSH-R. So it's the private key as it's copied from the keyring service. So I'm almost out of time, but maybe I'll leave you with a couple of philosophical points to dwell on. Last night, we were drinking some fermented beverages, and a friend asked me, so what do I go WOOT about, right? And I thought this was actually a really good question. And I think that what I want to try to convince you of is something I said at the beginning. Really, analysis is something that's not undisciplined or ad hoc, right? It's something that's quite deliberate, quite purposeful, right? There's nothing ad hoc or casual about offensive security. Okay, and I think maybe that's what I want to try to convince you of, or hopefully maybe we can argue about it in a second. The takeaway message really is, this is the last sentence of the paper, right? I think what I'd like to encourage maybe hardware vendors to do is rethink their approach to the memory management circuitry to make analysis a little bit easier. Because I think if you look at the history and the related work of interception techniques and memory analysis and monitoring, almost all of them are creative abuses of existing architectural features that are just not meant for this type of thing. So I think that artistry expresses a pent-up demand for better and more complete introspection facilities and hardware. So that's my 2 cents. Thank you very much for your attention. We really owe a debt of gratitude to Julian. He took a paper that was really rough around the edges and helped us polish it and get it to a much better shape. This work was supported by the Canadian taxpayer, and you can find all the code at Sarah's GitHub site. Thank you for your attention.
Hanno, did you think of, because I saw you have an Ethernet header in what was displayed, what uses do you think of by sending it actually on the network? I'm instantaneously thinking of quite a lot of uses from the dump we're seeing here. Does it actually contain the instruction, like the instruction string?
Yeah, very good. 2 good questions. So I think mostly our encapsulating this in an Ethernet frame, which is totally fake, by the way, right?
Yes, I figured.
Yeah, but merely for display purposes to make Wireshark swallow it a little bit easier. I think it's quite nice to think about leaking this as a regular network packet over whatever protocol you want to, whatever link layer protocol or physical protocol you want to. Your second question was about the instruction. Does it actually contain the instruction?
Generally, does it contain everything we see? Where
yes. So everything you see.
You can actually leak it as it is to the network.
Yep.
And so I could run, let's say, like a sniffer workstation on the network, and then instrument multiple machines with this on a different layer, and then correlate network memory events in, let's say, a multicast domain or something.
I think there's interest. I mean, we certainly haven't thought of all of them, but I think there are absolutely interesting ways to use this that we have absolutely not anticipated. Right? Yeah. Thanks.
Yeah. Hi, Michael.
Hey, Rick.
So, just really quickly, what do you consider a memory event? Is this something that, you're going to free some memory? What is a memory event?
Good. So I probably should have been more specific about that at the beginning. These are instruction-level memory events. So these are reads or writes of a particular number of bytes to or from a memory location. They are not system call level memory events or glibc level memory events as such, right? Big sequences of them are.
Mm-hmm.
Yeah.
Okay. So really, there must be some hardware that allows you to do this trapping, right?
Yeah. Right. So there's 2 things we rely on, basically. So I skipped over that because I didn't want to dwell too much on the details. But effectively, what we do is make use of the page table entry. Right? And so this is prior work. People have done this sort of thing before. Right? So we basically say this is a special page. The operating system handles that fault.
Right.
We have inserted code that says, is this a page Cage is interested in? If yes, go ahead and do the extraction.
Got it. Okay, thanks.
Perhaps I could make a remark. The last slide really resonated with me because one of my favorite things in this whole wide world is the APAX emulation of the NX bit by desynchronizing the ITLB and DTLB. I mean, it might seem pointless now that we actually got the NX bit, but this mechanics of using the fact that there are two fetch paths and two translation look-aside buffers, one for data, one for code instructions, and the fact that you can actually program that finite state machine. I've been not just a fan, a fanatic of this kind of thing ever since. I have no way of stressing this stronger, that yes, abusing memory automata has led us to much better memory processor features. And this continues. The SMAP is also informed by similar tricks, and hopefully we'll be able to take it even further. So, thank you.
I couldn't agree more.
I really love this tool. I see plenty of applications to it. One is intrusion detection. For example, you could have signatures just like people did like control flow signatures of programs. You could have signatures of memory events. Yeah. So you could actually log what is expected, the expected set of memory events of a process or even a kernel, and whether you see a divergence from that. So that's one application. Another application I see is reverse engineering of protocols. You could say, for example, okay, I can reconstruct a state machine of a protocol based on how many reads are followed by how many writes, and then how many reads again. And so you could basically recompute a state machine of a certain, interaction just like that. And if you couple that with the values that are read, then it becomes even more powerful. A third application I see, which is more nearest to my heart, is vulnerability detection. It's hard to detect vulnerabilities just dynamically. You need to couple it with something that would basically guide you to give you some coverage, maybe some kind of SMT solver or some other tool like that. That will basically allow you to explore the program properly. But this ability to basically record memory events happening in a program will allow you to find all kinds of things like time of check, time of use vulnerability. Somebody mentioned that earlier on. So you could say, okay, I'm writing this value at this pointer, and between the time that when the check is actually done, there is a first read to this value. Some check is done on it, and then maybe another read is done after that. That will basically make use of it later on. But maybe you can write to that value in between those two memory events, things like that. You can have also, you can imagine plenty of different heuristics for different vulnerability classes. Anyway, great work, Michael.
Cool, thanks. I think just a final comment. We're thinking of doing something very close to the first thing you mentioned, right? So I don't know how much I want to bend your ear, but thinking of modeling instances of types as what is done to them rather than what their names are, right? So you can think of finite state machines of activity related to a particular data item, right? Stuff like that. Thanks. All right.
We do have some more time. Anybody else want to ask anything? Okay.
If there is a LangSec workshop, will there be more of this at that?
That depends on Sarah. Possibly. Yeah. Thanks.
Thank you.